So if they ask you to define the resistance, you don't say the opposition to the flow of charges, rather you have to define it mathematically. Just like you define the Young modulus. So Young modulus is the measure of the strength of the object, but you don't define it like that. You say it is the ratio of stress to strain. So likewise, the resistance is the opposition to the flow of charges, but we define as the ratio of. Up next, we have the formula. So the standard one is resistance equals to voltage over current. And the other one, the more important one, resistance equals to rho L divided by A. So I'll be explaining this formula in detail. What does rho stand for, L, and what does A stand for? So the unit would be ohm, for which the symbol is this, and that also equals to volt per ampere. And sometimes, many of the times, they ask you to break down the unit of the resistance into SI base units. And in that case, you have to break down the voltage first. So you break down the voltage from this formula. Voltage is work done per unit charge. And then you break down force as work as F into D divided by charge. Now the unit of force would be kgms minus 2 base unit. And for meter it would be, for distance it would be meter, and for charge it would be ampere second. And then you can sort out whatever the final answer is. We covered that one already in chapter number 1. So I'm going to skip these ones. Just a quick overview. So for example, high resistance implies that more opposition to the flow of electrical charges, which are primarily electrons. And hence, the lesser the current. And for the low resistance, it would be the other way around. And then you have the water pump analogy. So just like in the water pump situation, there is a water pump that pumps the water, that provides the energy to the water. So the water would correspond to the current. The pump that provides the energy to the water would correspond to the battery, which provides energy to the charges. And in the example of water pump, the energy of the water is dissipated across the load. The energy that the water pump is providing is dissipated, is used to move the load, which is a water wheel. And in the electrical circuit analogy, the load is, it could be any appliance which is consuming the electrical energy. So once again, factors. We have covered this one topic in detail and filled all of that in the workbook of O-level physics as well. So here I'm just going to write down the final pointer, the length of the wire. And how does that affect the resistance? So the bottom line is resistance would be directly proportional to length. So what do you say? You say resistance is directly proportional to length. Instead of saying that if the length increases, the resistance would increase. So it is obvious that if the length increases, the resistance would increase. But above that, this is the next thing, that resistance is directly proportional to length. If we don't say that, if we just say increasing the length increases the resistance, then someone could be under the impression that the change in resistance would not be uniform if you change the length accordingly. The change would not be proportionate to the change in the length. So the ratio by which you change the length, the resistance would also increase by the same ratio. That's why we have to say resistance is directly proportional to length. Otherwise, just saying increasing the length increases the resistance would be a very general statement, and it does not give the real picture. Likewise, cross-section area, we have the reverse thing. The more the cross-section area, the less the resistance, and above that, resistance is inversely proportional to the cross-section area. And once again, the above blanks, you can just find it on the workbook of O-level physics electricity. And matter of fact, I have uploaded the video of this topic as well for O-level physics. If you want to complete those blanks, you can just do it from there. But I assume at this stage you would be all familiar with this already. So temperature. So when we say temperature, we are referring to the temperature in the case of conductors. So in this case, the change is, first of all, we cannot say increase in the temperature or the resistance is directly proportional to temperature. We don't have a mathematical relation between those two. They don't increase in proportion. But if you increase the temperature of a conductor, the resistance would also increase. And what's the reason? Increasing the temperature increases the kinetic energy of the molecules. They vibrate faster, they have more energy, they collide more vigorously, more frequently, and hence the temperature would increase. But for the conductors. And for semiconductors, for example, silicon and germanium, it's the other way around. So examples of some of the semiconductors is thermistor. So for these substances, for these materials, is exactly the reverse case. So what does that mean? If you increase the temperature, the resistance would decrease. For example, this happens in the thermistor. Now, last but not the least, if you have two conductors which are made up of, let's say here you have one conductor, and here you have the second one, and let's assume that these conductors have same dimension. Okay, they have same cross-section area, they have same length, and they are exposed to same temperature. For example, 25 room temperature for both of them. So everything is same except for the fact that one of them is made up of, let's say, copper, and the other one is made up of silver. Now the dimensions are same, the external factors are same, but they are made up of different materials. So their resistance would also be different. So we say the resistance, not only it depends on the dimensions, it depends on the material as well. So that property, the material, is measured by the stuff that we call resistivity, for which the unit is ohm meters. Ohm meter. So resistivity would be a material property, just like Young modulus, just like density, just like specific heat capacity, just like specific latent heat of fusion, specific latent heat of vaporization. And it depends on the atomic structure of the element. And by that, I mean the internal structure, the spacing between the atoms, the energy of the atoms, their orientation. So it depends on the material itself. So some of the material, for example, copper, it has low resistivity, and that's why we can use it for wires, and the materials which have more resistance, we can use them as heating element of the heaters. So here we have a sample question. Define the electric potential difference. So you can simply define it mathematically. Work done per unit charge. Now that would be it for 1 mark. But let's move on to the next question, which is rather more important. So we have to show that the resistance of resistance R of the extending wire is inversely proportional to A square. So how do we do? Let me write down the formula of the resistance first. R equals to rho L divided by A. And what we have to show is, we have to show this thing. Resistance is directly proportional to square of the cross-section area. Now let's check out the data. What we have is volume remains constant, and yeah, that's it. The volume remains constant, and the cross-section area is A. The resistivity is rho. So we have to get rid of the length here, because in order to convert it into this thing, you need to get rid of the length. So what we have is, let me write A as it is. So length can be written as, if volume of the cylinder, volume of the conductor is area times length, the cross-section area times length, then length would equal volume divided by area. So let me insert the value here. So I'm going to write volume divided by area. That area would be in denominator, and that equals to rho times V divided by A square. So R equals to rho V divided by A square. So the resistivity is going to be same, because you're not changing the material of the wire. The volume is going to be same. How do we know? It's given in the question. Over here, the volume remains the same. So if these two things remain the same, so they can be treated as a constant. So R equals to a constant divided by A square. And if I convert it back into proportionality, we don't write the constant, it would be this thing. Sorry, over here, divided by A square, but over here we have to write R is inversely proportional. My bad over here. R is inversely proportional to A square. So it would be written like this. Okay, R is inversely proportional to A square, and we have shown that. And keep in your mind, when the command word of the question is show that, you have to show all the steps, you have to show the working, you have to show when you change the subject of the equation. So you have to show this thing, the constant, and this formula, each and everything. So the second question is pretty much the same. You do the same method, except for you replace A, the value of area, with volume divided by length, and that divided by length would be shifted in the numerator, and you'll be getting L square, and hence you'll be proving this relation. So for Ohm's law, we have the statement that we, once again, this is being carried forward from O levels, and that reads the current passing through the conductor. All right, so there's nothing new in that. The more the potential difference across the conductor, the more the current flows through the conductor. So that thing can be written as this, and then you write it as V equals to IR, then you write it as R equals to V over I. So basically, this thing is not part of the A-level physics syllabus, but the actual equation from the statement, we should be writing this thing. And there should be a constant over here. I equals to a constant times voltage. Okay, could be, just let me write a constant here, times V. So it appears I equals to the product of voltage and a constant. But what we use is, we use this expression, V equals to the product of the current and the constant, which is the resistance. So basically, in this expression, the actual constant was conductance. And if you take the reciprocal of it, the conductance, the reciprocal of the conductance is resistance. So conductance can be written as 1 over R times V, and then you get the same equation, V equals to IR. But we don't discuss that in A levels. We just confine ourselves to these three equations. So let's have a quick go through this one. So R equals to rho L over A. You need to find the cross-sectional area. So in the question where the command word is show that, you have to make A the subject. The new subject has to be shown. Just keep it in your mind. Pay very focused to the question for which the command word is show. So the students thinks because the answer would be there for the question to show that, and it would be easy, so they forget about doing all the steps. So rho is the resistivity, which is over here. This is the total length, and this is the resistance. So all you have to do is to insert the values, and calculation would just be very trivial. Divided by resistance, which is 3.4. You hit it on the calculator, you'll get your answer. And then in order to find the current, you write down the value of the potential difference divided by current, V over R. It's the same thing as voltage over resistance. And for the next one, you have to find the average drift speed, for which the formula is I over NAE. For the average drift speed, for the average drift speed, this is what we have for the formula. So you just insert the values on the calculator, and you will be getting the answer. Let's take a look at the next one, the commentary based theoretical. Stain and explain qualitatively, so we don't have to quantify how the average drift speed of free electrons, where is that? Oh, okay, over here, in the thinner part compares with the rest of the wire. So for the thinner part, the cross-sectional area decreases. Okay, I'm just going to write the answer in bullets. You can just phrase it accordingly. Cross-sectional area decreases, and hence the effect on the average drift speed would be if I show you once again the formula for the drift speed, average drift speed. And why do we call it average drift speed? Because I told you already, there are plenty of electrons, millions and billions of electrons, and all of them may not be having the same speed. They have different speeds, so we have to take the average to compensate for different speeds. So I equals to V over NAE. E is constant because that's the charge of electron. N is constant because it's for the same wire, it's for the same substance. So if I decrease the cross-section area, if I decrease this value over here, the drift speed would increase. Up next, we have the other one. Once again, a theoretical. Stayner explain whether the power dissipated in thinner part is the same, less, or more than the power dissipated in equal parts of the wire for the rest of the wire. Okay, so for a quick recap, I'm going to write down the formula of power. Electrical power equals to I square R in terms of the current and resistance. And since current is constant, so the power dissipated would be depending entirely on the resistance, and resistance equals to rho L over A, as we explained just few minutes ago. And what is being done to the cross-section area? Well, the cross-section area for the thinner part means the cross-section area is being decreased. Hence, the resistance would increase, and if resistance increases, there would be more power dissipated.